Let us now see how we will simulate the primary converters. I will supply in the resource portion of the course website the simulation files for the buck, the boost and the buck boost converters. Here what we have discussed everything about the primary converters except that how to give the information signal, the gate pulse signal to the controlled switch. So what I have done here is that I am passing it through a PWM generator block during simulation and giving a voltage which is proportional to duty cycle. So if I want lower duty cycle, I will decrease the voltage, higher duty cycle, I will increase the voltage, and this will compare with a triangle waveform to generate the PWM, and these signals will turn on this BJT. So inside this PWM block, what you may find is that there is a triangular carrier. So this is, let us say, 10 kilohertz. I have set it to 10 kilohertz for now, but you can experiment with different frequencies. And this carrier is swinging from -1 to +1. And then you can have a control voltage, a voltage which is proportional to duty cycle. And then you will see that after comparison of these two voltage signals, the output that you will get will be something like this. So let us say all the at this comparison point, you will see that the voltage proportional to control voltage proportional to duty cycle is higher. So let us say we will have a high there, and then here the control voltage is lower than the triangle, and here it's higher than the triangle, so on. So as this control voltage moves up and down, you will see a modulation here happening in the pulses, and these are the pulses that will be given to the control, will be used as control signals for Q, and this is what you will be seeing at these points. Later on I will discuss in detail what goes into making the PWM so that you can build other PWM blocks and techniques. Let me now show you some simulation examples. In the resources folder, I have 3 folders, one on buck converter, one on boost converter, and another on the buck boost converter. And within them, I have the schematic files, netlist files, and the CIR files along with the edt01.sub. This is a subroutine subcircuit file. Now, when I open the schematic file, you will see something like that, buck.sh, and this is the circuit. So you see that I have here a switch, semiconductor switch, controlled semiconductor switch like a BJT or an IGBT. It's a generic switch, a VIN, a diode here, L, inductor, capacitor, and R0. And see here that I have a PWM module which is basically built of a triangle waveform, and I have a source here to represent the voltage proportional to duty cycle. So I have set it at 0.5. So 0.5 in a range of -1 to +1, approximately it is now 75% duty cycle. So let us see how this circuit simulates. I have put various node points. I have a node point here for the input, a node point here for the pole, node point for the output, and node point for the gate voltage. So to simulate, let us go to the command line, command terminal. I have opened the command terminal, and here we will run the simulation. I will use this and run buck. So it will create the netlist and then run the simulation and show the waveforms. Now what are the waveforms that I have here? I will indicate to you. Before that, Let me open the buck.cir circuit. So apart from the .trans statement, the include statement, I have this control statements where the background of the figure window is set to white, foreground is black, and then plotting the pole voltage, pole to output voltage, that is the inductor voltage, output voltage, and the inductor current. These are the things that are being plotted. So now back again to the plot, you will see that the plot goes through a transient phase here and then starts to reach the steady state. So you would like to look at the steady state waveform. So you can right click on the mouse and drag a very small portion on the steady state portion so that you will be able to see that portion only. So zoom that up. So this is the steady state portion, and you have green color is the IL waveform, pole to output is the inductor waveform, pole voltage waveform, V0 waveform. So you can study them in detail here. Take for example the green colored IL waveform, very small here. If you want to see, you can right click here and then amplify them by taking a zoomed small portion of that. It will zoom in and you will see that the inductor current wave shape as we had drawn while discussing the buck converter. So I will leave it you to explore, change values, change duty cycle, change frequency, change the values of the LCs, and then explore and try it out and try to learn about the buck converter. In a similar manner, I also have the boost converter circuit schematic here. So observe the boost converter circuit. You have the switch here, the inductor on the input side, diode here, and similarly I have the node labels here. You can also look at the inductor current. Likewise, I am having a control signal generation based on a sine triangle, based on a voltage triangle comparison principle. So this let us simulate. We will go to the terminal window, and in the terminal window let us run the simulation for the boost converter schematic circuit. It will generate the netlist, it will run execute, there will be a portion of dynamics, and then reaches the steady state. So what you could do is right click near the steady state. This has still not reached the steady state, but anyway you can observe. So take a small portion out of that, then you will be able to see it much better. Green is the inductor current, and you could probably have a look at the inductor current by zooming in like this. So it is just at the boundary of discontinuous conduction, but the waveforms as expected. So you can study this further, get greater insight by playing with the values and understand the boost converter. In a similar manner, I am going to show you the buck boost converter schematic. So the buck boost converter schematic is like this. You see the throw 1 to pole is this BJT or an IGBT, as you may consider fit, and throw 2 to pole you have this diode D. Look at the placement of the capacitance. Of course, this is the PSpice symbol showing plus here, but you will get a negative voltage. The buck boost will give you a negative voltage for as we had discussed. So let us simulate this. The PWM portion is like I had told for the other two converters. You generate the pulses by giving a voltage here proportional to duty cycle. Let us go to the terminal and let us run the simulation for the buck boost. It will generate the netlist and the waveforms, and you will see that the steady state is around the right side. Let me take a small portion of that, right click and drag an area, and you will get a zoomed portion of that, and this will give you a much better detail. So observe that output voltage, the blue line here, negative, it is on the negative side. Change the duty cycle, observe that, observe the values, observe the various waveforms. And if you want to have a closer look at the inductance waveform, this is the orange line here. You will see the inductor current waveform like that, slightly more amplified, zoomed, and then you see, as expected, you will see the waveform of the inductor current in this fashion. So again, I will recommend that you try to understand as much as you can by changing the values and by changing the frequency and probing at various points of the currents and voltages of the circuit.